In section 10.3, we're going to be looking at a number of properties of chords. And just to recap, what is a chord? Remember that a chord is a segment that has its endpoints on a circle. And if you think about it, since we've now talked about arcs, any chord, like this blue one here, divides a circle into a major arc and a minor arc. So this blue chord, we have a minor arc here and a major arc here. Same goes for any chord, except for a diameter, because diameter is the most important type of chord. Remember, a diameter has to go through the center. In that case, we don't have a major and minor arc. We have two semicircles. But in general, a chord divides a circle into a major and minor arc. And this first theorem says that in the same circle, or if you have two congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So if and only if, remember, works both ways. So if I knew that these two blue chords were congruent and they were marked with tick marks, that means that their minor arcs are congruent as well. So then I would know that these two arcs have the same measure and the same length. Okay? So if they're both, maybe they're both 100 degrees, who really knows? I'm going to put two tick marks, even though it's hard to say that those measures are equal. I'd have to name those. But yeah, congruent chords means congruent arcs, and that should make sense because a longer chord would be closer to the middle, and the arc would be bigger or a greater measure as well. And a really tiny chord, if it was out here, would have a very small arc. So same length chord means same arc measures. So let's look at that in an example. I'm told to find the measure of arc CD. Measure of arc CD, that's in this circle here. First of all, do you notice that the radius of each of these circles, circle P and circle Q, the radius is marked congruent. So I know circle P and circle Q are congruent circles. They have the same size radius. And the chords are congruent, A, B, and C, D. So now that we have congruent chords A, B, and C, D, then their minor arcs would be the same as well. So since the arc off of segment or chord AB is 100 degrees, then the arc off of that congruent chord here, CD, would also be 100 degrees. Okay, congruent chords means congruent arcs. In this example, if the measure of arc AB is 110 degrees, I'm going to mark that. Arc AB is here, and this is 110 degrees. Find the measure of arc BC, which would be this arc here. Well, notice these chords in this circle are both 9. So they're congruent chords. Therefore, their arcs are congruent and have the same measure, so arc BC would also have to be 110 degrees. I'm going to erase this for the second example because this one's a little bit different. If the measure of arc AC is 150, now arc AC, this would be the minor arc. It looks like that's the shortest arc between A and C. Then I need to find the measure of arc AB. Oh, wait a second, I'm missing two arcs here, and 150 has nothing to do with those chords. But don't I know that arcs BC and arcs AB would have to be congruent or the same measure because of the fact that their chords are congruent? So now I'm thinking, well, the whole circle obviously is 360. If I could figure out what's left for the rest of the circle after the 150 is gone, they are congruent, so I'll divide what's left by 2. So I'm going to do 360 minus 150, and I notice there would be 210 degrees left, but it's among two arcs that are congruent, so that divide that by 2, and the measure of arc AB would have to be 105 degrees. So these are both 105, which would together give you the 210 plus that 150 would give me the full circle of 360. So congruent chords in a circle means congruent arcs. New theorems here. This first theorem says if one chord is a perpendicular bisector of another chord, then that chord is a diameter. So I have this if-then here, and I want to mark what is given. If one chord is a perpendicular bisector of another chord. So I have a red and blue chord. One is a perpendicular, which means they meet at a right angle, bisector. Well, the blue one looks like it might be bisected, so then I would put these congruent marks. So if this happens, look, one chord is a perpendicular bisector of the other, and if you notice right now, the red chord is a perpendicular bisector of the blue one, then that chord, that red chord, is a diameter. Now to prove that this red chord is a diameter, what does a diameter have to go through? The center. So if I mark the center, now I know that red chord is a diameter. So if you see that happen, if you have one chord as a perpendicular bisector of the other, that chord must have been a diameter. And it kind of works the other way as well. In the next theorem it says, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So I'm going to start with the if and mark what I know. If a diameter of a circle, so if this is a diameter, it goes through the center. Now I have a diameter of a circle if it is perpendicular to a chord. So perpendicular would mean it meets at a right angle. Then I know that that diameter bisects the chord, meaning it cuts this chord in half, two congruent parts, and it bisects the arc, which would mean that these two portions of the arcs, those measures or those lengths, are also congruent. So that's kind of neat. A diameter, if it hits at a right angle to a chord, it bisects the chord and the arc. So we had two theorems here looking at diameter intersecting another chord. Let's use those here. Find BF, which is this length. All right, take a look at the picture here. I know that this segment AG is a diameter because it goes through the center C of the circle. This diameter is perpendicular to this chord. Now remember right back here, if a diameter is perpendicular to a chord, it bisects the chord and the arc. Therefore, it must bisect this chord DB since it is a diameter and it's perpendicular to it. So these two things are congruent. Now I know that 3x and 2x plus 5 are congruent or equal segments. And then I can solve for x, subtract 2x, 3x minus 2x is just a single x, and I find out that x is 5. But since I want BF, which is 2x plus 5, x is 5, so BF would be 2 times 5 plus 5, right? I'm plugging in x, so 10 plus 5, it looks like BF equals 15. And then DF should also be 15, and yeah, 3 times 5 is 15. All right. Next example here. Find the measure of arc CD, and find the measure of arc CE. All right, what do we have in this picture? Hey, once again, I have a diameter being perpendicular to a chord. So not only does it bisect the chord like we did here, but it does also bisect this arc. So I know that these arcs are congruent here, 9x and 80 minus x. So I'm going to set them equal. I know those are congruent chords, 90 and, I'm sorry, not 90, but 9x. 9x and 80 minus x are equal. And I have x on both sides. I'm going to add x, get it off of the right side. 9x plus another x is 10x. And divide by 10, and I find out that x equals 8. Alright, now that I know what x is, find the measure of arc CD. Well, it's 9 times x. We just figured out x is 8. So 9 times 8 would be 72 degrees. And then the measure of arc CE, now it should be double that, because remember how this was bisected? Do I get 72 degrees here as well? Well, yeah, 80 minus 8 is also 72. CE is either 72 plus 72 or 72 times 2, so 144 degrees. Okay, so this slide was using the fact that a diameter that's perpendicular to a chord bisects the chord and bisects the arc. This would be a real-life situation where you could use this fact that when two chords are perpendicular, one's a perpendicular bisector of the other, you have a diameter. Because in this situation we have 3 props placed on a stage at these points. I want to find the location so it's the same distance from each prop. Well, if I want to find wherever this magic point is, that's the same distance from all 3 of them. If you think about it, I need the center of a circle because then it would be like the radius. So if I want the same distance to all the points, distance would be like the radius of a circle. So I need to find what special point in that circle. I need to find the center of that circle so that we have a radius to each of those points. And how am I going to find the center? Well, I know a diameter goes through the center. So if you think, oh, a diameter goes through the center, if I had two diameters, they would have to meet at the center. And how can I find a diameter? Well, I'm going to go back. Remember that if you have one chord as a perpendicular bisector of another, that chord has to be a diameter. So if I do two chords and one's a perpendicular bisector of the other, then that chord would have to be a diameter. So first step, I'm going to create some chords. I'm pretending I'm already going to see a circle. So I'm going to make one chord, how about from Q to R, and I'm going to make another chord from P to R. And now I need to do perpendicular bisectors. Create perpendicular bisectors of those chords, because those would be diameters. And I know that diameters will meet in the center. Okay, so I gotta make this look the best I can. First of all, I know it's perpendicular, so I'm going perpendicular PR, but I need to be a bisector as well. So where is the center, the middle of that? Does that look pretty good, I hope? I'm trying to make a perpendicular bisector. And now I know that this is a diameter. And then I have to do a perpendicular bisector of this, QR. Okay, I'm gonna try to go perpendicular first, meaning a right angle. I think that looks pretty good for a right angle. But I also have to bisect it, so I have to go through the center. I think that looks pretty good. Another perpendicular bisector of this segment, 2 tick marks, different than this one. Now hopefully, if I did this right, this would be the center. This would be this magic point that is the same distance from each prop. And I can check that. I'm going to grab my circle tool back here where I have a center. And hopefully as I extend this, it'll go through P, Q, and R. Okay, that's pretty close. I'm a little bit off, but again, I just kind of eyeballed this, so I wouldn't expect it to be 100% perfect here. It's going through Q and R perfectly. P is just a tiny bit off. Maybe I can make that a little smaller and move it here. Okay, but that should be pretty close, and the distance then to all of those should be approximately the same here. If I look at like a dotted line here, there's a radius, and there's a radius, and there's a radius. Now actually, if you think back to chapter 5, when we did points of concurrency, we did perpendicular bisectors of the sides of a triangle, and they all met at this circumcenter, which was the center of the circumscribed circle. So we've done this construction before. Now we're just applying it to circles and saying that diameters are perpendicular bisectors of chords. So that's kind of neat there. And we got one more theorem to look at today. In one circle or in two congruent circles, you know that two chords are congruent if and only if, meaning it works both ways, they're equidistant from the center. And that should make sense. Now these red chords are congruent only if they're the same distance away from the center. If you think about it, if you're further away from the center, this is a much shorter chord because it's much further away. If you're closer to the center, the chord's going to be much longer. Okay? So the closer you are to the center, the closer or the longer the chord, and the further you are away from the center, the smaller the chord. If we are the same distance away, then the chords are congruent. So I'm going to mark these chords congruent, and now remember, if you're doing distance from a point to a line, what kind of angle do you have to go at? I have to go at a right angle or on a perpendicular here. Okay, neither of those look good, I'm sorry. Having issues. There we go. So if I go at a right angle, these segments are congruent if and only if these chords are congruent. So congruent chords means same distance from the center. Let's use that in an example. In the circle, I have two chords. Hey look, the distance from the center is marked congruent, and it is at a right angle, so that's legitimate distance from the center. I'm trying to find the length of this chord QR. Well, I have an expression for ST. That chord is 3x minus 1. I have an expression for QR, that's 2x plus 6. What do I know about these chords? If they're the same distance from the center, then they must be the same length. So I know that 3x minus 1, chord ST, must be the same as or equal to 2x plus 6, which is the length of chord QR. And now solve for x. If I subtract 2x and get rid of it from this side, 3x minus 2x is just x minus that 1, and now add 1 to both sides. And x equals 7. Oops, I can't put a box around that yet, because we want to find QR. And QR was 2x plus 6, so 2 times x, which is 7, plus 6, 7 times 2, 14, plus 6. It looks like QR is a length of 20. Let's make sure that we get the same answer here. 7 times 3, 21 minus 1 is also 20. It looks good. So today, properties of chords of circles.